Okay, so we met again on the second topic of the pattern recognition course, and we are now discussing the one-dimensional signal properties. This material applicable to any application of pattern recognitions where the data is a one-dimensional signal. So we will start with the sample applications, which is a little bit more detailed than the one that I gave you last week. But just like last week, I divided the section into problem domain, applications, and then input pattern and pattern classes. So the first sample applications and the last sample application is coming from medical diagnostic or medical area. The first example involves a signal from electrocardiograph, and the signal itself is normally called the electrocardiogram. So the signal is obtained by a contact from the sensor, which is connected to our body to measure the electrical activity of our cardio or our heart. So the input for this is the electrocardiogram, and the application is analyzing the electrocardiogram to determine any abnormalities related to the function of our heart. And then the second example is the EEG analysis, the electroencephalogram analysis. So it is a signal that describes how our brain's activities. Now, just an example, we could categorize the EEG signal into 4 different categories. One is the alpha condition, and then beta, gamma, and delta. And that is related to the frequency and powers of the EEG signals. So we can classify our EEG signals into 4 classes. Each describes the brain activities in gross. But we could also analyze the EEG in more details to determine something. Now, then I will jump to the last example, which is the tuberculosis detection. So the input is taken from a person's sputum, which is coming from the person's mouth, and then the sample is heated in a closed room, a small compartment, similar to the one that genus could be. We could add something to genus, for example, to get samples from volatile organic compound to determine if someone is positive TB or negative TB, means someone is detected as tuberculosis or not tuberculosis. Now the other 3 examples are coming from biometric, from other areas. So I'll start with the second row here. The biometric recognition, in this case, personal identifications, where the data is taken from our voice. And then, of course, the input to the system is a speech waveform, which means that the sensor needed for this is simple, which is the microphone. Then the output of the system is the person authorized to access something or not. And that is one example. Or simply the identity. But basically, of course, is the identity. Whether that identity is used for control access or used for something else, that would be depends on the application. Now, the next example, the speech recognition is trying to identify what is the word spoken by a person. So it could be a word, it could be a sentence, could be a spelling of a number, and so on. Of course, the input is also still the same, that is the speech waveform. Speech waveform is a signal generated by someone when he is speaking. So it is a pressure waveform. It's not electromagnetic waveform. Okay, the applications of these two could be combined, like the one which is used or which is developed by Microsoft for writing a meeting minute. This one. So who is speaking is taken also from the signal using the approach of voice brain. And then what is spoken by that or by someone then is also taken from the speech waveform. So at the same time, the system will understand who is speaking from his or her voice, and then what is spoken by her or by him. Now, the last example is speech recognition also, but applied to a different area. So, and now the speech recognition is applied to telephone directory. So we could ask the telephone directory something by voice. For example, if it is applied to some other area, it would be something like somebody is driving a car. He is alone. He would like to know where the gasoline pump, for example, the BBM station or gasoline station, and so he could just speak to the telephone, and the telephone will give the location, how to get there by voice. So in that applications, then signal is understood as a word, and then that word is understood by the system, and then get a response from the system. Normally the response is a written text, and then the written text is spoken by the system. So even though the input is voice and the output is also spoken words, but the spoken words written here is the response of the system. Okay, so before we look at the basic properties, we will start or we will review the generic process like the one that we have discussed last week, but it is now specific for 1D signal. So basic process consists of two parts or two phases. One is the reference building or training phase, and then the second part is the deployment phase or application phase. Now, on each of the phase, the steps is like the one listed here. So it starts by acquisition, and for acquiring a one-dimensional signals, we could use the microphone. Either it is a specific standalone microphone attached to an electronic appliances, or we could use microphone which is on our handphone. Now we could also use case sensors in case of applications such as the tuberculosis detections, genomes, also using the gas sensors. Then we could also use electrode. The electrode is used, for example, when we have an EEG analysis applications to determine whether our heart function normally or there is anomaly. The same thing as our EEG signal, electroencephalogram signal. Now, there could be other sensors, the one that we know, for example, for measuring the amplitude of signal from our Earth, which is used a lot by our friends in geophysics. Then we have the pre-processing. So once we have the digital signal, then we could pre-process the signal. So at the end of the acquisition, we will convert the signal into digital signal. And there is a sampling and quantization process which we will discuss shortly after this. Then we pre-process the signals. We could reduce the noise. For example, if someone speaking just beside the road on a roadside, then we could devise a noise reduction function to reduce noise from the road. So basically the road could be modeled as a signal with certain amplitude, certain frequencies, and so we could remove that noise. We may need a normalization in case we have several sensors, for example, and we want to normalize the performance of each sensor. So let's assume that we have 3 microphones from 3 different devices. Let's say handphone number 1, handphone number 2, handphone number 3. The position could also be different when we have data, even if the same data and recorded using telephones, then the signal would be different. So we have to normalize that one. Other possibilities is that we have, for example, we have a voice recorded with 8 kilohertz sampling and 16 kilohertz sampling rate. Then we also have to normalize this sampling. Okay, we might also would like to normalize a signal which is normally, for example, from minus 255 to plus 255 or minus 128 to plus 127, and we want to normalize it from minus 1 to plus 1. So that's also a kind of normalization. Then other normalization includes sample length. Now imagine that in order for someone to access a particular room, that person has to say certain magic words. Now, when he say now, for example, and tomorrow or yesterday, there is a possibility of the length of the signal would be different. So in this case, then we would like also to normalize the length of the signal. In that case, we might do the segmentation first and then the normalization. So then now we could discuss the segmentation. So what is the segmentation? Okay, when we have a system for access control in a particular room, now that system might be on for 24 hours a day and receiving signals anytime, even though it could also be designed to on only on a certain occasion. In the second case, then someone who would like to access a room, then he has to push a button, for example, and then speak. In the first case, that person doesn't have to push a button and just speak. Now, in the first case, the system has to know where the signal starts and where the signal ends. So it means that the system has to segment the data to find the region of interest of the signal. Okay, now after we have particular regions where the data lies, then we could extract the features. Now for 1D signals, then the features could come or could be extracted from the time domain representations, and it could also be extracted from the frequency domain representations. The time domain representation, I will show the signals might look like this. This is the amplitude, and this is the time. Okay, so our signal might be something like this one or something else. Then in the frequency domain, we will discuss this also later in detail. Just because I'm saying here time and frequency domain, there is a function is called the FFT, but we could also use the STFT, short-term Fourier transform. FFT, okay, and that the result of that transformation is we have a different representation where we have the power as a function of the frequency. So this would be probably something like that. Okay. Then of course we may have features extracted from these two different representation domain. Okay, after we have features from time, frequency, or time and frequency, then we could select some of them, which is more important for our purpose. Now, for this course, however, I will not discuss this thing because I think it will take a lot more time. So we will just assume that any features we extract from the time domain or frequency domain or combination of the two will all be used for matching. Okay, the matching, just like before, the one that we discussed last week, we could use a template matching, which is a one-dimensional template. So we have a template, for example, with a window length of, let's say, 8 or 16, or normally it is an odd number, or even a window of, like, say, 25. And now each time we measure a particular part of the signal with our template, and we measure the degree of similarity. If we find that the degree of similarity is high, then it means that we have a match. Okay, we could also use a statistical approach and a combination of statistical with artificial neural network, where the features are extracted from a statistical approach, and then the matching is carried out using the artificial neural network, or any combination that we have discussed in our first meeting. So with this, then we have discussed the acquisition, the pre-processing, the segmentation, feature extraction, feature selection, which is a minor one here, and then also the feature matching. Okay, so our one-dimensional signal could be described as consisting of a signal which has the amplitude, which is this height, that is from the very low part of the signal up to the top part of the signal. So this is called the amplitude. The amplitudes represent the strength of the signal. So the higher the amplitude, the stronger the signal. Then we have wavelength and frequency. And this picture on this sample, we have a signal which is start from here and ends here. This is called one wavelength. Consists of half cycle above the reference point and half a cycle below the reference point. Then we have the second wavelength, we have the third, and we have the fourth. So the signal consists of um, 4 waves. Now, if we have the time axis, let's say from here to there, then we can measure the time required for the signal to traverse this distance is, let's say, 1 second. Now, if this length is 1 second and it has 4 waves, then the frequency is 4 waves per second. So the frequency measures the number of cycles of the signal per second, or the number of waves per second. The wavelength and the frequency is related to the what is that? Intonation, if it is in a speech signal. So high frequency intonations means that the frequency is high and the wavelength, however, is shorter. So the shorter the wavelength, the higher the frequency. Now, if the signal travels through a medium, then there is a relation, direct relation between the wavelength and the frequency, because the speed of the signal traveling that medium is also known. Okay, and then the last property is what is called as the phase. The phase measures the relative position of one signal to the other. So just an example, if I draw a signal starting from top there and then going down here, and then after this one is and then going up here again. Okay, that one and so on. Then it means that this signal, the red one, the amplitude is the same as the black signal. The wavelength is also the same as the black signal, and so the frequency. The only different thing is that the phase. The red signal is said to be 90 degrees leading with respect to the black signal. So just to remind you that one full cycle is 160 degrees, because this the red signal leads only by half a cycle. It means that the red signal leads by 90 degrees. Okay, then here I showed you the electromagnetic spectrum. This also related to the material that we will discuss later in the course, which is the two-dimensional signal. The visible spectrum relates to that. Now, for our case now, it's just that I would like to say that our signals might be coming from any spectrum here. It depends on the application. For example, if we would like to identify an airplane, uh, then we could use the electromagnetic signal that is generated by the airplane's machine. The frequency could be very high, but if let's say we would like to generate, we have an application for the electroencephalogram or EEG or electrocardiogram or ECG, then the frequency would be very low. Okay, these are also group of frequency range where normally we have names for this particular area. Is of particular interest here is that we have a signal in the area of 20 hertz to 20 kilohertz. This is special because our ears could hear the signal only this area, only in this area. We could not hear a signal below 20 hertz, and we couldn't also hear any signal above 20 kilohertz. And that's why music is designed to use a full 20 kilohertz frequency range. However, our voice, if we are speaking like I am speaking now, then my frequency would be roughly only between 100 to 7500 hertz. Now, we will discuss later on here as an example of data sampling. Then we have higher groups of frequency, which is called the low radio frequencies or the AM broadcast. The AM stands for audio modulations. You might know this one in other course. most probably on the computer networking. Also, we have another group. It is from 3 megahertz to 30 megahertz, which is a high frequency radio, shortwave, CB, and so on. We have also 30 to 300 megahertz. It is a very high radio frequency for TV and frequency modulation broadcast or FM radio. And then we still have higher and higher. Now the tendency for the communication is to use a higher frequency range because if, for example, we have 1 bit per cycle efficiency, it means that one cycle brings 1 bit of information. If our frequency carrier is 300 gigahertz, it means that we could transfer data in the speed of 300 gigabit per second. Now, there is a finding in the United Kingdom that approximately 3,500 faster method of transferring data from the one that we have now. Now, with that speed, then the entire collection of Netflix would be able to be transmitted in less than a second. This is amazing, but however, this is still in the laboratory. So it will take a long time before it can be used on commercial application, before it can be used for our handphone, our communication network, and so on. Okay, just to give you an idea what is the frequency range means, other than the one that we have discussed before, is that we absolutely will not be able to hear anything at the frequency of 0, frequency of 10. Sorry, this is not the frequency, but the amplitude, the strength of the signal measured in decibel. Okay, rustle of leaves and very quiet wind is approximately 10 dB, so it's very quiet. Our quiet room is approximately 20 dB. The average room is approximately 40 dB, and conversations normally the strength of the signal is 60 dB. So if you are speaking, of if I am speaking very soft, then the dB, the strength, is equal to the average room, then we could hardly hear what I'm speaking or what you are speaking. Busy street is 70 dB, and then loud radio is 80. Train through station is 90 dB. Now you can imagine this. What is 90 dB looks like. Then 100 dB will cause our ears to be really painful, and 160 is damaging our eardrum. So never turn the music too loud, so it will it will damage our eardrum. Okay, now I would like you to note on this particular example that what does this very quiet room and then the power is 20 dB means. Okay, so let's take an example that we have an application which will be used on a white room. Now when our system is turned on, our system will receive a signal with the strength of 20 dB, and that is only noise. So we would like to neglect those signals. We are not interested to a signal of the power 20 dB or below this one. If there is a signal above 20 dB for our system, then it means that there is a signal, there is a data which our system has to be taken care of. For example, then process the signal. How to process it, we have discussed before. For example, where the start of the signal, and then try to predict what the signals is coming. So live prediction is also something that is of interest in the signal processing. For example, the application is something that is interesting. Let's say someone is speaking in Japanese, then we do not want to understand what he is speaking or he is spoken after he finished speaking. If it is possible, we would like to know what he is spoken at the time of he is speaking. At least, we'll say we are only one word late, so that we know what he is talking. Okay, so that is a research area by itself, and is now developed in many countries. Now, a signal, the one like the one that I'm producing right now when I am speaking, is actually a complex signal. However, these complex signals could be decomposed into its frequency components. Now, there is an example here where we have a complex signal. This is our complex signals. And if we decompose this signal, then we will find the individual components, which is this one. Okay, it consists of fundamental frequencies. It consists of a signal with twice as high as the fundamental frequencies, 3 times higher, 4 times higher, and 5 times higher. So let's suppose that this signal is 10 Hertz. The frequency is 10 Hertz. Then the second frequency component would be of 20 Hertz. 20 Hertz here, but the power is only half of the fundamental signal. And then the third frequency component will be 3 times as high, so it will be 30 Hertz. But the strength is only 0.3 of the fundamental frequency. The next one is 40 Hertz with the strength only a quarter, and then 50 Hertz and the strength is half. So now if we synthesize the signal, we add signal number 1, the fundamental, with the second component here, and the third, and the fourth, and the fifth, then the result is this signal on the bottom right portion of this. So, well, it means that we could see the signal as a complex signal consists of the uh, frequency components. This enables us to have approach on the frequency domain component. So that's why we could transfer this one, convert this one into the frequency component. So this is the frequency axis. We have, for example, the fundamental frequency of this power, and then the second frequency, the frequency is twice as high. However, the strength is only half. So I could draw here. So this is the to distinguish between the signal and the axis. I put an arrow there. Yeah. Then the third one is only 1/3, but the frequency is 3 times as high. And then the fourth one is a quarter only, and the frequency is 4 times as high. And then the last frequency is half the power of the fundamental frequency with the frequency of 50 Hertz. So this is the spectrum of the signal, which is of this form. So this is the time domain representation on the left and the frequency domain representation on the right. Okay, so after we obtain our signal, and then we have to process. Either the signal is recorded or it is live. But we have to do the same process. That is sampling and quantization. So let's assume that this is the analog signal. And then we do the first part, which is called the sampling. What the sampling does is reading or sampling the signal at a certain interval. The interval is constant, like the one shown in this figure. So it means that we have this value. I try to draw a red point, but it might not be visible to you. Okay, I try to write it a little bit bigger. So this is the sample of the the sampling result. The height of the signal, the power of the signal, but it is a fraction number. Now, normally our signal is represented in a number which is not a fraction. So we have to do the second part, which is the quantization. Now the quantization basically is converting from a fraction into integer representation. So now we have the value at this particular values only. The sampling result at this particular value only. So the number would be, if it is represented in 1 byte per data, would be 0, 1, 2, 3, 4, and so on up to 255. So with that, then we obtain a digital signal which exists only at a certain time, and also the value is also only an integer value. Okay, so the one that we process then, it means is a set of integer values, unless we normalize to a fraction again. Okay, so now what is the effect of sampling? Now, suppose we have a signal these upper figures. We have a black signal here, and we do the sampling as indicated by this circle. The frequency is exactly the same as the signal itself. It means that if the signal frequency is 10 Hz, we sample the frequency also at the speed of 10 samples per second. Then we will end up with reading the signal at exactly the same position each time. Now, when we store the result of the sampling and then we play back if it is a voice or a sound, we play back the result, and then what happens is that we don't hear anything. We hear only a single frequency, which is whatever frequency this one is. So because we only have this signal all of the same height, so we don't have a variation in our signal. Now, what if we sample at 1.5 times of the frequency? The example is shown below here. We have the signal, let's say it is whatever hertz, it doesn't really matter whatever frequencies, and because we sample at the frequency of 1.5 times, then we have a signal of the 4 divided 1.5, 3 by 2, 2 by 3 frequency, 2/3 of the frequency of the original signal. So the result is a signal of the dotted line. What this means, if we have a signal of frequency, let's say 30 Hertz, we sample with 1.5 times the frequency, then the sampled version when we play back is only 20 Hertz. It means that the frequency of the sampled signal is lower than the original one. So if it is a recording of a child singing a nice, beautiful song, then all of a sudden become a sample of voice, a song sung by an adult person with the frequency of lower. Normally the adult frequency is lower than the child. And this gives us well, this is not correct. So Nyquist has done a research and say that, well, if we want to sample, then we have to sample at least, this is at least, twice as high as the highest frequency component of the signal. Twice, minimum is twice. So in this case, if the frequency is 10 Hz, then we have to sample higher than 10 Hz. Sorry, higher than 20. Why? Because if we sample only at 20 Hz, then we could end up with this signal also, which is just a straight signal. Okay, so it has to be twice, at least, yeah, so more than twice. Okay, so this is an example. I will start with the lower quality first, which is called the telephone quality voice. Okay, just for your background, according to the European standard of public telephone, public switch telephone network, PSTN, the frequency carried by the telephone system is only from 30 Hertz up to 3400 Hertz. Well, I have just told you that our voice contains frequencies from 100 up to 7000 Hertz. Then when the telephone system only carried out from 300 to 3400. This is the European standard. Even the American standard conveys only 300 to 3000 Hertz, so a little bit less than the European standard. Now, the reason is that of this approximately 7000 Hertz bandwidth of our voice, it might look like this one, the figures. Okay, so this is the power. This is the frequency. 300 is probably about here. 3500, 400 is approximately here. So now you can imagine why the telephone company decide to bring the signal only from 300 to 3500 is that most energy lies on this area. It means that the other signal is not conveyed. It will not really disturb for the purpose of communication. I will still understand what you are spoken, and you will also still understand what I am speaking, because majority of the signal is brought to you or from you brought to me. We lack only of the very low frequencies and very high frequencies. So what are the very high frequencies? It is used a lot in singing or people are angry and so on. So if you try to win a contest of singing through telephone, then you would have to manage your voice in such a way that your voice is only from approximately 300 to 3400. It has no meaning that you are trying to reach a very high frequency from you to sing at, let's say, 6000 Hertz. Why? Because it will not be delivered to the jury. Okay, so the telephone companies only conveys the signal from 300 to 3400, and in regards to the Nyquist frequency, so the sampling rate of 8000 Hz will be sufficient. Now remember that 3400 multiplied by 2 is 6800, and 4000 Hz is above 6500. So basically all the signals from 300 to 3400 are sampled with a very high quality. Okay, so now the other example is the sampling of what I'm calling here as the high quality recorded voice. Now we are trying to store all the frequency components that is generated by a human being, which is from 100 to 7500 Hertz. If we sample the signals with 16,000 Hertz, it means it's larger than 15,000, which is twice as high as 7,500 Hertz. It means that all the frequency contents is sampled, or the signal is preserved. Okay, so we have a very high quality voice. Now, the one in the bottom is said that, well, what if we have music signals? Now, when music signal is designed to use 20 kilohertz full range, it is because of our voice, but it is because of our ears. Our ears could hear a voice or a sound from 20 up to 20,000 hertz. And for that one, we have to sample the voice with 42k hertz, which is a little bit higher than twice of 20,000 hertz. Now with this sampling rate, it could preserve the voice, the sound of a music. So sound of music is well documented with a sampling rate of 42k hertz. Okay, now we mentioned a little bit about noise. Now noise could come from many different sources. One noise, if it would be considered noise, is when I am teaching just now, and all of a sudden, let's say a motorcycle pass nearby my house. It will generate a noise, and that noise is not from the source, but the noise is coming along the transmission line. The first transmission line is, of course, from my mouth to the microphone, and then the signal is deteriorated with motorcycle noise. Now, the other noise is coming from the quantization. Remember that part of the sampling was quantization, the second step. At the sampling itself, we have a signal in a fraction. So basically, there is no noise there. But when we quantize on into the nearest integer, then we introduce a noise, which is half of the interval on the quantization. So let's say that we sample the signal with one bit only. It means that the result would be either 0 or 1. Any signal higher than a half would be represented as 1. Any signals below a half would be represented 0. It means that the noise is, well, the maximum of the noise, quantization noise, is half of the height of the bit itself. If it is 1 millivolt, it means that the noise will be half of a millivolt. Now the measure here is said to be signal to noise ratio. This one is SQNR. Quantization noise ratio, signal to quantization noise ratio. The expression is simple. It is 10 multiplied by a log, and the base is 10. The signal square divided by the noise square. Well, in reality, we never know what the voice is, but this expression would be very useful if we model a method to reduce the noise. So we have the original signal, and then we could add a noise using our model, and then we apply a noise reduction using our model. Then so we could measure what the noise like. Is it totally removed, or it is only one portion of it is removed from the signal. Now the square could be moved to front, so that in the second part of the example, of the equations, the expression become 20 multiplied by log 10, the strength of the signal divided by the strength of the noise. Now, if this expression is applied to quantization noise, then the expression is become 20 log base 10 to n minus 1. So n is the number of bits used for quantization. So if it is an 8-bit number, then n would be 8. So the SQNR would be 2 power 7 divided by half, or would be 14 multiplied by 20 n dB, or we could say 6.02 multiplied by n dB. So that's the quantization noise. Now, if we use a high number of bits, then it means that the quantization noise would be very small. But if the number of bits is very low, let's say 2 bits only, then the quantization noise would be very high.